Hey everybody, welcome back to another video lesson. Today we're going to go ahead and take a look at what's called strength of acids. The strength of an acid depends solely on its ability to break up into ions. Now I know that doesn't seem like it makes much sense, but that's how chemists look at the strength of an acid. It doesn't depend on how much reactivity it has or how its ability is to dissolve things or be corrosive or any of that kind of stuff. It just solely looks at how many ions it can put into solutions. We focus on, as we did before with the acids, the hydrogen ion. So we've got an acid over here. It's dissolved in water, and the little notation here, the red represents the hydrogen ion, the green represents the anion, and this could be a chloride, it could be a bromide, it could be a nitrate, and this represents the whole acid in its molecular form. So when we drop the acid into the water, okay, what it's going to do is it's going to dissociate. Now, each acid dissociates to a different degree, and that's what we're referring to when we talk about the strength. So over here, this acid breaks up into ions, okay, and stays intact. Now, if we contrast that to the acid on the right-hand side, this acid over here is dissociating completely into ions. We get almost all ions and actually, in this case, no molecular species whatsoever. So we would say that this acid is a lot stronger than the acid on the left-hand side because it has a higher concentration of hydrogen ions by itself, not in the molecular form. Remember, the acids are going to break up and dissociate, and the strength tells us how far it dissociates, how many ions it's actually producing in solution. So if we were to test the conductivity of this solution, this one would be way higher in conductivity because there's a lot more ions in the solution than there is for the acid on the left. Okay, since each acid has its own ability to dissociate to a different degree, we're going to have weak acids and strong acids. Well, before we get to that part, we need to talk about 7 special strong acids. These are acids that are so strong that they completely dissociate into ions, and therefore their ions are there pretty much is no molecular species whatsoever. Now, there's 7 acids that you need to know for this, and those are hydrochloric, hydrobromic, hydroiodic, nitric, perchloric, chloric, and sulfuric acid. Those 7 acids, anytime you put them in water, they're going to always completely dissociate. So what that means is that if we're looking at the equilibrium of the reaction, the equilibrium is going to favor the product so much that we pretty much can ignore the equilibrium altogether because there aren't going to be any of these left in solution. They're almost all going to be put into this side. So this is a reaction where the equilibrium favors the product so heavily that we don't really need to worry about an equilibrium whatsoever, and we don't have to have a K value for this. So this is why these are special, because there's no equilibrium. We're going to be able to treat these as if it were a standard reaction that goes to completion. So we're going to say that the hydrochloric acid, when we put it in the water, it's going to react completely with the water, so that the HCl would be our limiting reactant in a sense, and we can do a BCA table to solve this. Same thing with this one over here. But these are pretty much the same reaction. We're just dropping out the water. A lot of times we're going to write the reaction like this. So you have the HCl is going to go to 0, and it's all going to be ions. So whatever the concentration of your HCl is, the hydrochloric acid, or in this case any of the 7 strong acids, the hydrogen concentration is going to be the same. So when we deal with our strong acids, something like HCl, the concentration of that acid is going to be equal to the concentration of the hydrogen ion every single time because it always completely shifts to the right. Makes these really easy to work with. The pH is really easy because all we have to do is calculate the concentration of the hydrochloric acid, which will be this, and then plug into the pH. And I'll get to the calculations a little bit later. All right, so let's contrast that to the weak acids. Now we deal with the weak acids because weak acids are actually going to be shifting to the right just a small little bit. We're actually going to have equilibrium established because the products are going to build up and they're going to start to convert back into those reactants. So you're going to get equilibrium when we deal with the weak acids. So any acid that is not one of the 7 that you have to know can be considered a weak acid. So anything outside of those 7, weak acid. Therefore, what that means is you're going to have to treat these as if they were an equilibrium system. Therefore, they're going to have a Ka expression. A Ka I'm going to get to in just a little bit is referred to as the acid dissociation constant, and it works just like any other K. So when we have weak acids, we're going to have equilibrium established. When we have the strong acids, no equilibrium. And this is all due to the relative strength of the acids. Okay, so let's take a look at that a little bit more closely. So the acid dissociation constant tells us the relative strength of the various acids. Now, this is where things get a little confusing. We have weak acids, but of those weak acids, some of them are stronger than the other ones. Okay, these are not the 7 special strong ones, so keep that in mind. So if I have a hierarchy of weak acids, I can determine which acid is stronger. Now remember what the definition of a strong acid is. A strong acid is one that dissociates more, produces more hydrogen ions, right? Essentially what that means is that the stronger the acid, the more it favors the products. Therefore, it favors the products more. The value of Ka will be higher and higher for those stronger and stronger acids. So the stronger the acid, the higher the Ka. Now that makes sense because when we get to those 7 strong acids, those reactions we said, remember, shift so far to the right that they are pretty much considered no equilibrium because the acid itself approaches 0. Well, if that approaches 0 at the bottom, then Ka becomes undefined, and there really is no Ka value for strong acids, for the 7 strong acids. So you don't have to, usually that's a dead giveaway because the problem won't have a Ka value for the strong acids. All right, we'll get to the calculations and strategies for that in the next video lesson. Okay. So the relative strength of the acids depends on the value of the Ka. So I can have these various acids here, and I can see that hydrofluoric acid is the strongest of all of these acids. Now when you're looking at Kas, and anytime you're looking at scientific notation, you first want to make sure you look at the number up here in the top right hand corner. This number here is going to tell you. Now this means that that's 0.000724. So the number here tells you how many zeros essentially are in the front. Well, if there's more zeros in the front, because this is going to have 4 zeros before the 1, this will have 6 zeros before the 4, means that the number is getting smaller and smaller. So the bigger the negative number, right, the larger the magnitude of that negativity, the smaller the value, therefore the weaker the acid. So these acids are getting weaker as you go down the list. Now, when you compare numbers that are the same to the same -4, that's when you look in the front. You look at the numbers here. Most of these, it doesn't matter that this is 7.24 when I compare it to the HBRO, because this is to the -9. That's got 5 more zeros in front of the 6 than this one does. So therefore, this is going to be a lot stronger acid than the HBRO. Okay, so that's how you read the acids. That's how you deal with Ka. So the larger the Ka, the stronger the acid. The smaller the Ka, the weaker. And again, that's based on the equilibrium and what's favored and what's not. Okay, so thanks for watching the video lesson. If you could, appreciate it if you could hit that like button. Thanks a lot, guys. Appreciate it.